Okay, a short presentation. Luca Gallo got his PhD at the University of Catania with Vito Latora and Mattia Frasca with the thesis coupled dynamical systems in presence of higher order interactions, and in 2022, and for a couple of years he got a postdoc position at the Central European University working with Federico Battiston, and since a few weeks, if I understood correctly, he's still in Budapest, but now at the Corvinus University, and now, today, Luca is going to give a talk about the synchronization of chaotic oscillators with higher order interactions. Please, Luca.
All right, so good afternoon, and thank you for joining, and thanks to the organizers for inviting me today to give this talk. So as Paolo said, this presentation is titled Synchronization of Chaotic Oscillators with Higher Order Interactions. As you see from the title, there is a lot to unpack, and I promise you that at the end of this presentation, you will have at least an idea of all the elements that are here in this title. All right, if I have to start from the very first word, which is synchronization, I guess all of you, at least once in your lives, have experienced synchronization, where you were at a play or at a concert and you started clapping. And while at first you were clapping on your own, after a while you realized that you were clapping in a coordinated fashion with all the other people in the crowd. And so this was synchronization, but synchronization is not just about people clapping. It can be also about fireflies who can synchronize their flashes, like this species that are typical from Southeast Asia, and create these beautiful waves of light in the forests. But besides these cheerful and beautiful examples of synchronization, sometimes synchronization is a dangerous phenomenon. For instance, the neurons in our brain can sometimes synchronize their activity, and this coherent behavior is associated to epileptic seizures. So in this particular case, synchronization is something that you want to prevent. And from this example, I mean, there are two take-home messages. The first one is that synchronization is almost everywhere. It appears in a variety of systems that are very different from one another. And the second message is that synchronization is something that can emerge from the interaction among the units of a system, not necessarily with an external control. It can emerge spontaneously. And I'd like you to start from a very typical and well-known model for synchronization, the Kuramoto model, in order to convince you about this spontaneous emergence of synchronization. In the Kuramoto model, you have a population of n coupled oscillators. Each oscillator is basically defined by a number, a phase, whose evolution in time is determined by a natural frequency, and each oscillator has a proper natural frequency, omega I. So when they are isolated, these oscillators just spin on their own. But then you have a coupling term. You let the oscillators interact with one another. And how does this work? Imagine you have two oscillators, I and J is faster than I. So what I does, feeling the presence of J, is to accelerate in order to keep up with J. And the other way around, J instead decelerates in order somehow to wait for I. And the strength of this interaction is tunable and is tuned by a coupling strength, which here is called K. So when we, by changing the value of K, we can change the collective behavior of the system. When the K is very low, meaning that the interaction among the units is weak, as I said before, all oscillators basically spin on their own. But when K is large enough, you can see that the system starts moving collectively in a coherent way. And there you can have synchronization. So with this simple model, we realize that it is the strength, it is the interaction among the units that can let the synchronization state emerge. But the Kuramoto model has one missing element, And the fact is that in the chromotor model, all oscillators interact with one another. But in general, not all units of a system interact with one another. If you think about the neurons in our brain, again, they follow precise patterns of interactions. And the presence of complex patterns of interaction is again something very common in a variety of systems, in physics, in biology, in engineered systems, in social systems. And because of this ubiquity, the theory of complex networks proved to be fundamental to study the behavior of such complex systems. And through the lens of complex network, the dynamics of a system is basically shaped by the patterns of interaction that exist among the units of the system. All right, so for those of you who are not familiar with complex networks, they're actually a very simple mathematical objects, and they are a collection of two sets. There is a set of nodes, each representing a unit of the system, and a set of links that represents instead pairwise interaction among those units. And to encode the information of a complex network, you usually use the adjacency matrix, which is a matrix n times n. N is the number of nodes, whose elements I, j, are either 1 or 0, and they are 1 if the corresponding units I and j are connected by a link, and they are 0 otherwise. And from this adjacency matrix, we can define two quantities. The first one is the degree of a node, namely the number of connections the node has. And from that, we can define the Laplacian matrix, which is a very important matrix that has on the main diagonal the degrees of the nodes, and on the off-diagonal terms basically is the adjacency matrix. And why is that so important? Because it is associated to a variety of dynamical phenomena unfolding on top of the complex networks, including diffusion, random walks, and as I will show you, synchronization. Right, so complex networks for decades have proved to be a great tool for studying complex systems, but we also realize that they have some limitations, and one of them is the fact that they are not able to naturally encode group interactions, which is something that emerged in many systems. And what do I mean by higher order or group interaction? Let's take this example coming from ecology, where there are 3 species, a shrub, a bulb, and a grass. And the higher order interaction here is the fact that the shrub do not affect directly the bulb or the grass, but it influences the way in which the bulb acts on the grass. And this higher order interaction cannot be fully encoded using a complex network. We need to go beyond. We need more complex mathematical structures. And this is why in our work we relied on the complex hypergraphs. These are probably less known objects, but they are very similar to networks, and actually they are a generalization of networks. You have again a set of nodes and a set of hyperedges. These hyperedges have different sizes or different orders. An hyperedge of order 2 represents a two-body interaction, and it's basically a link. An hyperedge of order 2 represents a three-body interaction, and so on. So you have multiple orders of interactions, and because of that, to encode the structure of a complex hypergraph, you need a set of adjacency tensors in this case. So you have more objects compared to the complex network, but these objects they look very much the same. For every tensor, you have elements that are either 1 or 0. They are 1 if the corresponding units are connected by a hyperedge, and they are 0 otherwise. And if you take this definition, if you put d equal to 1, you recover the standard adjacency matrix. Right, so from these adjacency tensors, you can define, again, a set of degrees, which count the number of hyperedges of different orders that are connected to a node. But also you can define what we call the generalized degree of a link, which is basically the number of hyperedges that includes 2 nodes, I and j. And with these 2 quantities that you have for every order, you can now generalize the notion of the Laplacian matrix and define a set of generalized Laplacian matrices for the various orders of interaction. And this is a good generalization, because if you put d equal to 1, you again recover the standard Laplacian matrix for networks. All right, so enough with how to encode networks and hypergraphs, let's talk about dynamics, because synchronization is all about dynamics. I will not start directly from synchronization on hypergraphs, because it will be pretty hard to follow. Let me first start from synchronization on networks, which is very similar and quite easier to understand. So imagine, as for the Kuramoto model, you have n oscillators that are now coupled through a complex pattern. And the state of this oscillator is encoded by a state vector xi, whose dynamics is governed by two quantities. You have a function f, which determines basically what the oscillator is, how the oscillators behave when isolated. And this can be very simple, like it could be a natural frequency, but it can also be something very complex, like a chaotic system.
So, Luca, scusa, sorry if I interrupt you. I don't know if it's just my problem, because my graphics is very bad to see the slides. I don't know if also other people have the same problem. If it is just my problem, okay, it is not so important.
For me, it's fine.
Okay, so it is my problem of mine. Okay, no problem. Okay.
All right.
Okay.
I'm sorry for you, Paolo, but
okay.
I hope it will get better. All right, so I was saying this function f can be something more complex. It can be a chaotic system. So I don't know whether you are familiar with those kind of systems. They are very weird in the sense that they are highly sensible to initial condition. They are very hard to predict, and they do not have a periodic, let's say, motion. Although they still have something called a strange attractor, which is something in the phase space, is an object in the phase space which attracts the trajectory of the system. Though these strange attractors are not periodic, one example of them, probably the most famous, is the Lorentz attractor for the Lorentz system, is the object you see on the bottom left of this slide. And the cool thing, despite these objects are so complicated, we can still synchronize a system made of them. This is very, very cool from my point of view. And all right, so this was the function f, and the second term that you have in this equation, in the system of equation, is the coupling term, which now you can recognize, for which now you can recognize the elements already, because it's similar to what I showed you for the Kuramoto model. You have a coupling strength, which is now called sigma. You have a coupling function telling us the way in which the units interact, and here I chose a particular scheme of coupling, which is called the diffusive-like coupling. It's a difference between two functions, and now you have also the structure of the interaction through the adjacency matrix. All right, so how can we study synchronization using a system of equation? First, we need to realize that there is something called a synchronization manifold, which is a trajectory in the phase space that all units are able to reach. And this trajectory is defined by the function f. And note that each unit is identical, so all units have the same function f governing their motion. And so they are all, since they are identical, they are all able to reach the synchronization manifold. So for a system to synchronize, it means that if all units are, let's say, a bit far from the synchronization manifold, eventually, if we let the system evolve, they will converge and go back to it. So what I'm doing with this idea is try to frame the problem of synchronization as a problem of stability. It is the stability of the synchronization manifold. And to study the stability of this trajectory, what we can do is to analyze the motion of the perturbation from this synchronization manifold. So what we do in practice is that we linearize the system I showed you, and we end up with a system of equation that you see in the bottom left of the slide, where you can now you can recognize the Jacobians of the functions f and h, and you can clearly see where the Laplacian matrix comes into play. Right, so this is a system of linear equations that are still coupled, and this is hard to let's say to deal with, because imagine you have millions of units, billions of units. Like in our brain, we have thousands of billions of neurons. It's very hard to integrate such system. And so what we would like to do is to reduce its complexity, because it would be very hard also for I mean, I am not talking analytically, I'm talking also numerically. And to reduce the complexity of this problem, what we can do is to project the system onto the eigenbasis of the Laplacian matrix. And by doing that, we decouple the system of equations, finding n linear equations that are now decoupled and are all determined by one eigenvalue of the Laplacian matrix. These are the equations in the box. And let's have a closer look. The first of these equations, the one associated with the smallest eigenvalue of the Laplacian matrix, which is 0, trust me on that, is basically the equation telling us where the synchronization manifold is. This is the dynamics tangent to the synchronization manifold. The other n-1 equations instead governs the dynamics of the perturbation transverse to the synchronization manifold. So because we want all units to go back to the synchronization manifold, what we would like to have is that the perturbations along this direction will dump out in time, right? So this is the first thing. The second thing I would like to put your attention on is that we started from a very general complex network, and now all the information on the structure of the network is summarized in a set of eigenvalues. And so we have a great reduction of the complexity of the structure of the network. And the third thing is that this n-1 equation describing the motion along the transverse modes all look the same up to the value of the eigenvalues. And so instead of studying n-1 equation, we can actually study one single equation, this master stability equation, in terms of a parameter alpha. And to study the stability of this equation, we can evaluate the maximum Lyapunov exponent, which will be in terms of this parameter alpha. And this is what is called the master stability function of the system, which depends just on the particular chaotic, not necessarily chaotic, but the particular oscillator we are considering, so the function f, and the coupling scheme we are considering, and not on the network anymore. And I'd like to, again, to tell you, we started from a system of n coupled nonlinear equations, and now we are studying synchronization through one single linear equation. That's a great achievement from this theory, which is the famous master stability function approach. And what can this master stability function tell us? If you look at the red curve, you see that this master stability function is always positive. So for every value of alpha, you will have that the perturbation along the synchronization, perpendicular to the synchronization manifold will grow in time. So for any value of the coupling strength, for any structure, this system will never synchronize, okay? If you look instead of at the green curve, you see that the master stability function, which is first positive, then becomes negative. So it means that if alpha is large enough, namely if the coupling strength is large enough, then you can synchronize the system because the perturbation will degrow in time. So what is this? This is basically the Kuramoto model. It's the same idea. But beside these two, you have a third case. Actually, you have more, but I will stop on 3, which is the blue curve, where the master stability function is negative in a given value of alpha, in a given interval of values of alpha. And so if the coupling strength here is too weak, then you don't synchronize the system. If it is too strong, you don't synchronize the system either. And so there is a sweet spot where you can synchronize the system. And also note that the thresholds for this master stability function are determined by the eigenvalues of the Laplacian matrix. So it's not possible in general to synchronize any complex network having this kind of master stability function. All right, so this was the work of Pecora and Carroll for the master stability function approach on networks. What we did with our work was to generalize this framework to hypergraphs. And to do that, we first started by writing down the system of equation governing the motion of oscillators coupled through pairwise and higher order interactions. And you can see that we have additional terms. Those are the one in the box. So the system is way more complex, but you recognize at this point all the elements that we have already talked about, which are the coupling strengths, the coupling functions, and also you have the patterns of interaction in the adjacency tensors. So the system looks very similar with to the previous one. So let's try the same analytical treatment. Let's first linearize the system, and if we do that, you end up with the equation in the system of equation in the box. It's I mean, trust me, it's a system of equation just in a more compact form, where it's evident where the different Laplacian matrices for the various orders of interaction come into play. And now we would like to decouple this system of equations, but this is not possible in general, because the Laplacian matrices in general do not commute and do not share a common eigenbasis. So it seems like we are stuck, but actually, there are two special cases that we identified where we can still perform an analytical treatment. The first case is the one in which the Laplacian matrices actually commute, and there are some peculiar higher order structures where this is possible. But if you want to keep some generality in the patterns of interaction, instead you have to put some constraint on the coupling functions, and this is what we did through what we call the natural coupling hypothesis, which is, I mean, I will not go in detail, but it's the hypothesis that you see in the box. And if this hypothesis holds, then you can define a multi-order effective Laplacian matrix, this matrix M, which summarizes, let's say, the contribution of all orders of interaction. And with that, you can now rewrite a new master stability equation that works the same as for networks, but now instead of having the standard Laplacian matrix, you have this multi-order Laplacian matrix. But now you can decouple this system of equations. And let's see how we can do that using the Rosler system. The Rosler system is another chaotic oscillator. It looks very periodic, but actually you have these bumps on the z-axis. This is a highly nonlinear and very unstable system. The attractor is what you see in the animated picture, and on the right you see 9 different master stability functions that we derived coupling n Rosler oscillators through different coupling schemes that are pairwise and free-body. You realize that there are let's say what we call type 1, type 2, and type 3 master stability function. And for the next slide, I will focus on this particular coupling scheme, which is a type 3 master stability function, which comes from the fact that we couple the Rosler oscillators through the x variables. And I mean, having that coupling scheme in mind, let's see what happens with some numerical simulations, because so far this was the theoretical framework we have developed, but a good framework is such if it is able to reproduce I mean, the real world, but in our case, the real world meant the numerical simulation. So what we did was to take a complex hypergraph, which is the thing you see in the box. Actually, you don't see the hyperedges because otherwise this figure would be a complete mess. But for every triangle of links that you see here, there's also a hyperedge. So the possibility for the nodes, which are Rosler oscillators, to interact in a 3-body way. And we let evolve the system considering different values of the coupling strength, sigma 1 and sigma 2, and monitor whether the system synchronizes or not through a synchronization error. And so if this error is 0, it means that the system synchronizes. If it is not 0, then it means that it's not coherent. And as you can see from the figure on the right, our theoretical framework is in a good agreement with the simulations. Indeed, if you look at the red curve, the area within this red curve is let's say the values of the parameters sigma 1 and sigma 2 for which we predict a negative master stability function. So the synchronization of the system. And as you can see, this well predicts where the synchronization error goes to 0. But we also did other numerical tests with other oscillators and with other coupling schemes, but I mean, I will not go into detail for all of them, but if you have questions, ask me anything. I will just go to the conclusion, which is that with this presentation, I showed you how it is possible to formulate, say, to derive a formalism to study coupled dynamical systems in networks and higher order networks or on hypergraphs. And I showed you how we could use this formalism to study the synchronization of chaotic oscillators in particular, and through the so-called master stability function approach, which again is something that we generalized to the case of higher order networks. And this theory is very powerful, and we proved its validity and generality through multiple numerical simulations on complex hypergraphs. And so, I mean, you can use it if you like, if you're interested in this kind of applications. And I mean, to conclude, I'd like to give you a reading list. And if you're interested in knowing more about that, you can check these 3 papers that we wrote out of this framework. Also, there is this I showed you through this presentation is the cornerstone of my PhD thesis, which is online, and I can send you the link if you're interested. And I mean, you can drop me an email if you have questions that you don't want to do now. And I'd like just to thank all the great people that helped me making this, let's say, this work come true. So thank you.
Thank you very much, Luca. So, Steve, Davide? No. Okay, see, yeah. Davide, you can speak. Davide, perhaps now you have your okay.
Now it was disabled the possibility for me to reactivate the microphone. I don't know why.
Okay, but now you can speak.
Okay. Thank you very much. Now, just to know, if I understood, your system is a purely dynamical system without noise.
Yes.
The typical approach. My question is, what do you expect that can produce? For example, the basic noise, just I don't know, Gaussian white noise. If can change in a significantly way.
Okay, so this is something so thank you for the question because it's very interesting. It is something that we haven't explored. I think it can change, of course, the behavior of the system. I mean, I'm guessing here, because of course the synchronization manifold have, let's say, a Bayesian of attraction. So probably if you add noise, this Bayesian of attraction will change. So I am pretty confident that the noise can have an impact on the, let's say, on the master stability function itself. But I am guessing, but that's my opinion on that.
But you didn't try?
No, we did not.
Okay, thank you.
But if I can add just a short comment, it should have very interesting effect in the dynamics of the network. If you study the dynamics, the chaotic dynamics, normally is just already know that noise can put the system to visit some part of the phase space which are less probable to be visited. The dynamics will be very rich.
Definitely. Thanks.
Okay, so, Luca, I have missed one point. Can you show the slide with the classification of master stability functions?
Yes.
I have missed what is the difference between, I mean, what's the future, the parameter making the difference between type 1, type 2, and type 3?
So the difference is here, basically. So, for instance, if you take the Rosler oscillator, as I showed you, this JF will not change. But if you change the coupling scheme, it will change the function H, and so it will change the JH. And I mean, with different coupling schemes, you could have different types of master stability function. But actually, with different types of the function F, I can show you actually this picture. So here we changed the coupling scheme. We changed the H. You can see that in let's say, the titles of the panels. You see that there are different values for the H2. H1 is basically the same. And you see that by varying that, you're varying the profile of the master stability function. This is what make change the master stability function. Of course, if you change also F, for instance, if you take the Lorentz system, then it's a completely different story. So these are the two things that make the master stability function in a way or another.
Okay.
I don't know if this answered your question.
Okay, thank you.
Right.
Okay, If there are no other questions, I would thank again both speakers, and I think that they have been both successful to give a pedagogical introduction to their talk, and for this reason I thank them. And okay, so see you again next month.